Hello, thank you for being here at Image, and thank you, David and Scott, for introducing me. I've got a personal interest in salt domes in the Gulf of Mexico around the Houston area. When I started my career, I worked for Arco Oil and Gas in the late 1980s, and I learned a lot about geology working in the Houston area and the onshore salt domes. And my career was like a lot of people's. After the salt domes became less an exploration target for larger companies, we all moved offshore into the deep water Gulf of Mexico, and I worked even more salt domes. So now that I'm retired and for working for Star Creek Energy, I came back because I realized that some of these salt domes probably had a lot more exploration potential than people have given them credit for. I see a tremendous opportunity to revitalize the onshore salt dome play. And seismic data has vastly improved since the 80s when I worked it. And I think that you could use seismic to find new salt traps in some of these domes. And they've been hidden for years because the area is full of salt domes that either haven't been shot with modern seismic or haven't been reprocessed. So here you see in my introductory slide, I like to go visit some of our landmarks in the Houston area. There are several salt domes to the south of us, and I'm visiting one called Damon Mound, pointing to it. And then here's an oil well that's south of Houston and West Columbia. So there's definitely some day trip options. The overview for my talk is we're going to talk about the evolution of these salt domes, and we're going to talk about, so Houston was basically founded on salt dome exploration, and the salt dome exploration was from the 1930s to the 1960s, but honestly, the seismic technology was terrible. And we're going to review some examples of seismic data then and now. And as certainly I remember in my career, around 1980, the whole industry left to explore the much better imaged salt domes of the offshore. But around the year 2000, seismic imaging technology has improved, I think, to amazing levels. But there's also a puzzle on these salt domes. A lot of the Piercement salt domes look kind of similar in many ways, but some are highly productive, they're giants, and others, they look pretty similar, but they're just not that productive. So my question was, is this a technology problem, or are there truly some fatal flaw in all these domes? Or, you know, let's just take a look in detail at some of the domes, and I think you'll follow me along to these conclusions. So here's a map of Houston. The green area is the greater Houston area, and the red dots are 33 vertical piercement salt domes that I've looked at. And they're, just so you can tell on this USGS strat chart I'll put on the side, all these domes are surrounded by the Miocene, the Frio, the Yewa, and Vicksburg, and the Wilcox. So the Wilcox is Eocene, and the Frio is a Legacy. So none of these wells got anywhere near the Cretaceous. The Alston Chalk area is up to the north, and I assume they're all Jurassic oil source rocks. You may have heard about some of these domes. We're going to look at some highly productive domes, Humboldt, Barbers Hill, and Spindletop, and some less productive domes like Hockley. So this graph shows the Houston area salt dome production to date, and it's from the USGS site, and it's in millions of, it's from the Railroad Commission site, and millions of barrels is on the y-axis. And you can see they're not giant fields. Humboldt, Spindletop, and Barbers Hill aren't giant fields, but they're subgiant fields, with Humboldt being, almost 200 million barrels to date. Barbers Hill is about 180 million barrels to date. But you'll see that beyond the big ones, they quickly tail off into being under 10 million barrels or even 5 million barrels. And so this was a question that stumped a lot of people, is that some of these domes look kind of similar, but why are some so much more productive than other wells? So here's a close-up of the Houston Beaumont study area. And I did put the cumes on the salt domes. You may look at where your house is. You know, how far are you from a salt dome in the Houston area? Personally, I live up near the Hockley Salt Dome, but if you live down near the Astrodome, you live near the Pierce Junction Salt Dome, or up in the Woodlands, you are south of the Woodlands was the Humble Salt Dome near the airport. So let's go on. Well, one thing you can see right away from even a preliminary study is the salt dome aerial size is not correlated with the total production off the domes. In fact, some of the larger domes, which Bowling Dome is just south of Houston and San Felipe is over near Katy, are huge domes, and yet they don't produce that much. Whereas the mighty little Spindletop, which is only 700 acres, produces a tremendous amount of oil. And Barbers Hill, again, about 2,000, 3,000 acres, produces a lot. So strangely, you may not have expected this, but the size of the dome is not correlated with its productivity. And let's look at the first dome, which is the Humble Salt Dome. Now, Humble was found by the same man who found Spindletop. His name was Petio Higgins, and he found Spindletop in 1901, but by 1903, he was over here in Houston, and he had stake locations on the small hill that would become the Humble oil field. Now, Humble oil field was not productive in the cap rock, so it took a couple of years till they found oil on the sides of the dome. But this is the field that was a major producer during World War II and put Houston and Texas on the map. It's produced 168 million barrels. It's still active today, mostly in the development stage. There was a wildcat recently drilled on the northwest side. I'll show you a picture of that. But of course, it launched major oil companies. The Humble Oil, which was created by Petilla Higgins, now has merged into Exxon, and also the companies that became Gulf and Texaco had their fortunes here in Humble oil field. So Humble oil field inspired a lot of artwork. Many people think of all domes look like Humble oil field. I like this picture from the East Texas History website because Humble oil field, when you make a cross section, is a very thick stock. It doesn't neck off into a balloon during any down to at least 20,000 feet. So it's sort of the model of what people think of when they think of salt domes. And you can see depicted on the top of the dome many, many closely spaced wells that are intersecting oil pays on top and around it. Obviously, one of the models for the Houston Geological Society emblem was probably the Humble oil field, and that was this logo was designed in 1949. So this is a map on the Humble's top Frio, and I made this using well control, and we have a line of cross section I'm going to show you, and we know that there's a salt overhang on the northwest side that was actually recently drilled to the Wilcox and found some gas, but the dome is it's a thick stock down to at least 12,000 feet. And one thing it's very prominent over regional dip. For example, there's a syncline down on the southeast side, and if you measure the syncline level at 2,850 feet to the top of the dome, it's 750 feet tall off regional dip. And it's also blessed with very abundant and porous reservoirs. And if you check out some of the older literature from, let's say, Hal Booty's book, called Salt Domes of the Gulf Coast in Mexico. It has a very complicated shatter pattern across the top of the dome. So let's look at this cross section. So the northwest side is on my left here, and you can see a digitized well, and there's quite a bit of good reservoir on the sides of the dome. Another thing you'd like to see is that these beds, even with the well control, just correlating the well control, they all thin up onto the dome, starting in the Miocene, and then through the Oligocene and the Yewa, and even in the Wilcox things, all these formations thin up onto the dome. So this dome was relatively rising faster than the deposition around it, or conversely, deposition was falling faster than the dome was. Uh, it's a salt technology question. So here we're going to talk about the Humboldt Salt Dome, and I have some visualization things I'd like to show you. So when you look down on it, it looks like a pin cushion, and it does produce oil from all sides. It has very high quality Miocene and Frio sands, and when you look around, it's just there's like over 2,500 wells drilled, and the vast majority of 65% are listed as oil producers, and I think the dry holes are probably just caprock wells because it's pretty hard to find a dry hole on Humboldt oil field. We're going to take a look now at Spindletop oil field, and that's located to the east of us in Jefferson County near Beaumont, Texas. So I like this thing. Spindletop is the giant under the hill. There's a great book you can buy called Giant Under the Hill, and you can get that at an online bookstore. Discovered in 1901 as one of the first oil fields by Patillo Higgins, who lived near Beaumont. And this regional top Frio map shows that, again, the Spindletop is not a large area, a large dome, but it is very tall. It's if you subtract the syncline in front of it from the top, it's over 900 feet tall, and it has great trapping to the north. There's almost a rim syncline up there you can see here on the southwest, and then a very deep basin in the front. So Spindletop is going to trap hydrocarbons just because it's such a prominent feature over dip. So here's the top cap rock salt, and about half the oil production from Spindletop comes from an overhang on the southwest side, and there's an interesting story with that. So they thought that Spindletop was going to produce from the top of the dome, which is Miocene anhydrite and carbonate, but that reservoir was quickly depleted. And about 1925, the Yount Lee Oil Company drilled some of the first wells that went through the salt and went down into a pocket on the southwest side, and that turned out to be a highly productive pocket. Let's just take a look at, for example, if you look at some of the logs from the pocket wells on the southwest side, these are stacked pays of 50 to 70 feet of solid oil, and it does not take a large aerial space to pack in millions of barrels. Also, the Frio and the Miocene is very porous here, and so these are high quality reservoirs. So this cross section across Spindletop the cross-section across Spindletop shows the southwest side. See all the wells there on to the left, and the little stars indicate the pay in the Frio. And not only is it very tall well, it's a tall feature, it's also got a lot of thinning onto the dome. So the two stars on top represent that early phase where they produce blowout wells in the cap rock, and then the southwest side is under an overhang, and it produces about half the production in the field down there. And below the Frio is pretty shaly, as indicated by logs. So here's an example of what Spindletop 1970 seismic data looks like. So you can see this. It's a publicly available seismic line if you go to the Gladys City Boomtown Museum in Beaumont, and it features what people had to work with back in the 70s with seismic data on domes. All those arcs at the top are poorly migrated reflectors, and then this vast incoherent area where there's a dome in there somewhere. It's really hard to believe that people drilled a lot of wells based on using seismic, and I think it disappointed a lot of people because the quality of the seismic was so poor for many years. Now, I've got permission to show this is a 1990s 3D seismic line over the same interval. It's got south on the left here, and now the top of the dome is imaged a bit better, and the overhang is now visible. So I'll have the next slide. I'll have some interpretation on it, but the dome is imaged a lot better. So if we go to the next slide, I placed the dome in like this, and you can see the Miocene and the lower Miocene, the Frio and the lower Frio are all thinning quite dramatically up on the dome, and sort of depicted where that salt overhang pocket was penetrated back in 1925. So how do we really know what any kind of salt dome looks like? I think that a lot of the domes have not had the benefit of good seismic processing, and I think there's hidden traps on the old salt dome. And these older pre-stack time migrated data, it still isn't imaging the sides of the dome to the detail you would need to find, like, say, a new trap of oil. So, I think one of the things the industry might consider is reprocessing seismic data or even shooting new seismic data over these all onshore salt domes, because in this example from Interpretation Magazine, you can see that it is now possible to image the salt overhangs in detail and create these 3D models as given to me here by Zterra. They're, a very complicated velocity model that will result in better quality seismic. So here's some examples of modern seismic processing improvements. This one is from SEG Interpretation Journal, and I think it shows probably what some of these vertical ones like Humble or Spindletop would look like if they had the benefit of this pre-stack, beam migration processing or reverse time migration processing that's now really relatively commonplace in the offshore, but is hard to find any examples of it on onshore wells. So let's take a look at Barbers Hill. That's my case study number 3. And Barbers Hill is out in the far east side of Houston. It's also known as whatever. And now Barbers Hill has its famous salt dome overhang is actually on the east side. And this cross section shows that one of the reasons this is such a productive oil field is that it's got such great sands in it and so many multiple pays, and it's also pretty tall over regional. So this overhang is a pretty deep pocket. I'm going to show you an image, and is extremely productive. So here's a regional top Frio map on Barbers Hill. And you see one of its great trapping features is it's got a rim syncline to the north, and it has a lot of thinning up onto the dome in all the directions. So here's a cross section where you can see the cap rock of Barbers Hill, and now it has a very pronounced and kind of unique salt overhang on the east side that's produced a lot of oil from the Miocene and the Frio. So one of the things that kind of surprised me about Barbers Hill is that there's just not a lot of deep drilling on Barbers Hill. Most of these wells end about 6,500 feet, and they have a couple wells that indicate some shaly Vicksburg, but it's not a dome with a lot of deep exploration on it. So here's 2 cross sections, one from the literature of 1955, and then here's my workstation cross section from the top assault mapping. And you can see that this dome has a very unique overhang on its side that's actually a big, very robust pocket for uh, for hydrocarbon entrapment. And so, it comes to mind, like, what if we had actually good seismic that on the domes like this? I think there's a lot of opportunity that's not being taken advantage of. Now let's talk about a challenging dome, the Hockley Salt Dome. It's up north of Katy on the west side of Houston, and it's only produced 1 million barrels. Now, you may have heard of Hockley Salt Dome because there is a active salt mine there. It's a very small hill. You can barely see it, and it's right next to a bird wildlife refuge called the Katy Prairie Conservancy. A lot of people go out there to see migrating birds, and from the tower for watching birds, you can see the salt mine down there, and it's called United Salt. So here's a cross section across Hockley Dome. And the salt mine goes down to about 1,400 feet in the cap rock. But there's a wells that have been drilled. Actually, there's like 500 wells on Hockley Salt Dome, and I'm depicting one that's on the southwest side. There's a small overhang there. This is probably where most of the 1 million barrels has come from, and it has a Frio section and a lower Miocene section of sort of thin, discontinuous sands. So there really aren't any tests below the Yewa and Hockley Dome, so people still are interested as possibly being productive. But let's just take a look at the regional mapping. So if you map the Hockley Salt Dome at the top of the Yewa or the base of the Frio, you'll see the overhang on the southwest side, and you'll note that this just doesn't have a lot of thinning onto the dome. So let's take a look at this cross section A to A prime. So A to A prime, Hockley Dome probably has a leak problem all around the dome because it's just not that tall a dome. If you subtract the syncline in the front from the top, it's only about 300 feet, and you have some strong regional dip that's going up toward the north and northwest here. And as actually Michael Halby pointed out in his book, he thought that Katy Gas Field was actually a more prominent structure and may have taken hydrocarbons away from Hockley Dome and filled them in Katy Gas Field, which produces at the Wilcox. So I've tried to depict with multiple arrows here that Hockley Dome has a trap problem on regional dip, and also a low producing dome is the San Felipe Dome, and that's 5 or 10 million barrels, all produces off the southwest side. And so that also has a problem perhaps with the ability of hydrocarbons to migrate away from the dome into other structures. So now let's compare the Barbers Hill Salt Dome with the Hockley Salt Dome. And the Barbers Hill has much more production than Hockley, yet they both have Miocene and Frio reservoirs on either side. Both domes are surface expressions, and both domes have cap rock, and both domes have been discovered 120 years ago. But Hockley lacks the thinning that you see on Barbers Hill, and it lacks a very significant overhang pocket compared to the Barbers Hill uh, hydrocarbon pocket. And I think the about reservoir quality on Hockley from the logs that I saw was a little bit less quality reservoir. So those things all combined to make it a somewhat challenging exploration dome. So the conclusions I have here is that highly productive salt domes have to have that stacked pays, they have to have multiple pays, the Miocene Frio and Yewa need to thin onto the dome where they'll have strong traps. And the best salt domes are very tall off regional dip to the tune of hundreds of feet. And salt overhangs make great traps. Now, less productive domes, uh, some of them have they just don't seem to thin onto the dome. And we can discuss, salt tectonic models. I think the salt body was there through history, but the region, maybe its surrounding sediments were just on keep up, and they just didn't push down around the sides of the dome to make the thinning. And it's very critical to look at regional mapping when you're evaluating these domes, because if you're just making a small study around the domes, you probably can make what look to be prospects against faults. But if you take a look at the regional, you can see leak points, based on well control and seismic that may be fatal flaws on some of the lower producing foams. So you want to have a big overhang, you want to have thinning on the dome, and you want to have high standing dome against regional dip. So I want to thank everybody that helped me on this. I've got some references cited, and I want to thank this Robert Pledger for his salt domes and Z Terra for those depth imaging